For the last page of Lesson 1, we're going to look at equations and determine using set notation only the domain of the function. Okay, first one, we're going to move through this somewhat rapidly. We know that radicands have to be positive, so I know that x minus 2 has to be greater than or equal to 0, which leads to our set notation x such that x is greater than or equal to 2. That's our answer. The second one, y equals 3 over square root of x. Well, we know that the radicand has to be positive, but we also know we can't divide by 0, so in this case, x has to be greater than 0. X such that x is greater than 0. Number 3, y equals the absolute value of x plus 5 over x plus 5. There are no restrictions in the numerator, but there is a restriction in the denominator because you know that the denominator cannot equal 0. So our set notation will be x such that x cannot equal negative 5. Y equals the square root of 5 minus x. This is just more a cautionary example. Our radicand has to be positive, but when we solve this, we're going to subtract the 5 and divide by a negative, and when you divide by a negative, it flips the inequality symbol. So x is going to be greater than or, I just said it and then didn't write it. So we're going to say x is going to be less than or equal to positive 5. Number 5. Oh, this one is a little bit more interesting. X squared minus 4. Radicand has to be positive. Now let's watch when we solve this one. I'm going to add 4 to both sides. Now, do you remember that if I'm taking the square root of both sides, then I get the absolute value of x, principal square root, is greater than or equal to 2. And that, you should remember, that means two different pieces. So we'll write x such that x is less than or equal to negative 2, or x is greater than or equal to positive 2. You probably learned that in an algebra class. You should have learned that in an algebra class. Example number 6. No restrictions in the numerator. The denominator, thankfully, is factored for us, which makes it a little bit easier. And the denominator can't equal 0, and there are two quantities that would make this equal to 0. X minus 3 cannot equal 0. 3x plus 5 cannot equal 0. So our answer is the set of all x such that x cannot equal 3, x cannot equal negative 5/3. I like this problem here. The denominator cannot equal 0. Alright, so I am going to subtract the 16, divide by negative, or I can add this quantity. In the end, we're going to get x plus 2 quantity squared cannot equal 16. We'll take the square root of both sides. And the principal square root comes into play here. So we have the absolute value of x plus 2 cannot equal 4, square root of 16. So x plus 2 cannot equal 4. Also, x plus 2 cannot equal negative 4. So that's going to give us our answer. It's going to be the set of x such that x cannot equal 2, x cannot equal negative 6. Number 8 is my favorite example on the page. There are two restrictions. In the denominator, we know that x plus 4 has to be greater than or equal to 0. The radicand has to be positive. And then in the bottom, we know that x cannot equal 1 because we can't divide by 0. So we need to make sure we write this domain that includes both of these restrictions. So our answer is going to be x such that x is greater than or equal to -4, but x cannot equal 1. Perhaps you wrote it as follows. You may have said -4 is less than or equal to x is less than infinity, and then comma, x cannot equal 1. Both of these are acceptable. One of the things for AP Calculus that are absolutely essential is knowing what graphs look like. Y equals the natural log of x is no exception. You have to know what this function looks like. This function, let's label our x and y axis. This function has an asymptote at 0. It crosses at a special point and then continues to grow slowly, but growing nonetheless all the time. This special point here is the x-intercept 1, 0. That tells me that the natural log of 1 is 0. The natural log of any value of x greater than 1 will be positive, and the natural log of any value between 0 and 1 will have a negative return. Our domain is going to be the set of x such that x is bigger than 0. You could have written 0 is less than x is less than infinity. But the function is only defined for positive x values. In number 10, we are going to consider what we looked at number 9 and some translations of that. So the 5 is going to vertically stretch this, but that won't have an impact on the domain. This will have an impact. That is going to shift it to the right. So here's our critical point of 1, 0, but if we shift it to the right 2 values, then our y-intercept is now the point 3, 0, and we have a new asymptote. Instead of the asymptote being the y-axis, or x equals 0, our asymptote shifts over 2 as well, here. And our new graph, again, it's a vertically stretched one. Okay. So it's going to look more like that. So our domain, x such that x is now greater than 2. You can see the importance of knowing this graph in order to come up with a domain of other functions with the natural log that are translations of that parent function. Number 11, the sine of x. You should certainly know what this graph looks like. It goes through 0, 0, it comes up, sinusoidal. This is not the prettiest sine graph I've ever drawn, but you get the idea. The domain, x is an element of the reals. I'll use set notation and say x such that x is an element of the reals. In number 12, we look at the tangent function. Now, the tangent function, like the cosecant function, has a whole bunch of asymptotes. And then it keeps on with the pattern. Asymptote over here, keeps on with the pattern. Now, you have to know a thing or two about this. It's going to have asymptotes where the cosine equals 0. So you should know that the cosine is going to equal 0 at this pi over 2. And then if I go out a distance of pi, we'll have our next one. If we go out a negative pi, we'll have our other asymptote. So you have to think real carefully on how to write this domain. It's a set of all x. Do you remember we have to here write what x cannot equal? It would be impossible to write every possible interval because there are an infinite many. So we'll say that x cannot equal, that's a little tricky, see if you can figure it out, it's going to be pi over 2 plus pi times k, where k is an integer. Last example, y equals e to the x. That's no different than y equals 2 to the x or 3 to the x. It's an exponential function. The asymptote is the x-axis. It goes and then grows exponentially. This has the y-intercept 0, 1. You must know this graph. And of course the domain here is x such that x is an element of the reals. X can be any real value. The function is defined for any real value of x.